Hello everyone, and welcome to the video on section 2.6 on rational functions. The objectives in this video are 1, to find the domain of rational functions. Number 2, determine any vertical, horizontal, or slant asymptotes. And the third one will be to graph rational functions. Our conceptual objective is to interpret behavior of a graph as a rational function approaches an asymptote. First of all, let's look at the definition of a rational function. A function f of x is a rational function if f of x, which equals n of x over d of x, such that d of x does not equal 0, where n of x and d of x are polynomial functions. The domain of f of x is the set of all real numbers x such that d of x does not equal 0. So in other words, what we're really looking at when we determine the domain is all we're going to be looking at is our denominator function and identifying the places where that thing is equal to 0. Wherever it's equal to 0 is going to be not part of our domain. Let's look at a couple of examples. The first one, we want to find the domain of f of x equal to x minus 3 over 4x squared minus 4x minus 5. So what we're going to do on that, in this case, we want to go and factor out that denominator. We want to factor as far as we can. So in this case, it'll be x minus 3 over x squared minus 4x minus 5 will factor as x minus 5 times x plus 1. So in this case, the domain of f is all values of x except for 5 and negative 1. So we're going to have the interval that goes from negative infinity to negative 1, union negative 1 to 5, union that with 5 to infinity. That would be all values of x such that x does not equal negative 1 or 5. In the second example we want to find the domain of g of x, where g of x is equal to x minus 2 over x squared plus 9. Well, really what I'm looking at is the values of that will make my denominator equal to 0. So I'll set x squared plus 9 equal to 0. And notice when I solve that, I get x squared equals negative 9. So x would end up being plus or minus 3i. Well, our domain has got to be real numbers, and since the values that make the denominator 0 happen to be complex numbers or imaginary numbers, in this case, for function g, the domain is going to be all real numbers. So it's all reals, and the interval would be from negative infinity to infinity. Now let's start looking at asymptotes. Asymptotes are lines that the function begins to approximate. So these asymptotes can be vertical, they can be horizontal, or slant. So we're going to start out looking at vertical asymptotes, and then we'll move on to horizontal and then to the slant asymptote. The first one, vertical asymptote, the line x equals a. So it's a vertical line. X equals a is a vertical asymptote for the graph of f of x if f of x either increases or decreases without bound as x approaches the number a from the left or the right. So as x moves closer and closer to a, so in this first graph that I have right here, as we move closer and closer to a, notice our graph is going way up. So in this case, this is an example of a function that is increasing without bound as x gets closer to a. Over on the second one, we see an example of a function that's actually decreasing without bound as x moves closer and closer to a. Be aware that this type of behavior can happen on either side. There's a lot of different things that could happen with that, but as long as it's happening on one side, that will be classified then as a vertical asymptote at x equals a. The question now is, how do we locate a vertical asymptote? Well, if we let f of x equal n of x over d of x, and as long as that's in lowest terms, so there's no common factor between the numerator and denominator. If there's a common factor, things get a little bit different, and we'll talk about that in class next time. But if this fraction, we're going to assume it's in lowest terms right now, then f of x will have a vertical asymptote at any real 0 of d of x. In other words, any place the denominator is equal to 0 is going to be a vertical asymptote. Let's look at an example. F of x is x squared over x minus 5. In this situation right there is no common factor between the numerator and denominator. So I know I'm going to have a vertical asymptote whenever the denominator equals 0. So I'm going to just set x minus 5 equal to 0, and I will get x equals 5. So in this case, I will have a vertical asymptote at x equals 5. Our next asymptote is a horizontal asymptote. So we're going to say the line y equals b is a horizontal asymptote of the graph of a function of a function if f of x approaches b as x increases or decreases without bound. So what we have, you see a couple examples where we would have a horizontal asymptote at y equals b. In this case, in this first one right over here, at this one, we are going with a function f of x, and it's, you notice as x goes far away from 0 to the right, my function is getting closer and closer to y equals b. So y equals b would be a horizontal asymptote. The second one, notice we're actually going through and we get the horizontal asymptote as we move off to the left. The other thing that this illustrates, though, and I want you to be aware of this because there's usually a misconception here, vertical asymptotes will never be crossed by a function. It's not going to happen. But notice a function can cross a horizontal asymptote at some time. So it is possible for us to go through and when we graph a function that has a horizontal asymptote that we will actually cross that asymptote. And so don't be alarmed or confused if we go through and when we graph it we actually do cross a horizontal asymptote. That can happen. Now the question is, how do we locate horizontal asymptotes? Well, to do that we're going to have a lot of writing, but you'll notice that I've put some things in red and blue on this slide, and that's key information for us in determining if we have a horizontal asymptote. So we're going to start out here. We're going to let f of x equal n of x over d of x, our standard rational function, but now we've written out that polynomial using that definition of a polynomial we've seen in the past. So n of x is going to be a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus plus a sub 1x plus a sub 0. And we have the same type of thing with d of x, only we're going to use b's for the coefficient, and our degree of that denominator is going to be m. So the degree of the numerator is n, degree of the denominator is m. Now, the way we go through and determine about a horizontal asymptote, we're going to look at just n and m. If n is less than m, in other words, if the degree of the numerator is smaller than the degree of the denominator, then we're going to have, then the x-axis, y equals 0, is going to be the horizontal asymptote for that rational function. If n equals m, in other words, the degree of the numerator and the denominator are the exact same value, then we're going to get a horizontal asymptote, and what that horizontal asymptote is going to be is just the ratio of those leading coefficients. So it's just going to be a sub n over b sub m. Just those two numbers right there, that fraction. That will be the horizontal asymptote. And if n is greater than m, then there is not going to be any horizontal asymptote. Let's take a look at a couple of examples, 3 examples here. We're going to start out with f of x. f of x is equal to x squared minus 4x over x cubed plus 1. Now notice in this case the degree of my numerator is 2, the degree of the denominator is 3. Since the numerator has a smaller degree than the denominator, I know I have a horizontal asymptote, and that horizontal asymptote is just going to be the x-axis, or y equals 0. In G, we have g of x is 3x squared plus 7x minus 1 over 5x squared plus x minus 4. Notice in this case, degree of my numerator and denominator are both 2. Since they're equal, I know that there's going to be a horizontal asymptote, and in this case, the horizontal asymptote is going to be the line y equals the ratio of their leading coefficients. So in this case, y equals 3 over 5. In the third example, we have in that one, the degree of the numerator is 3. The degree of the denominator is actually 1. So in this case, the degree of the numerator is bigger than the degree of the denominator. And when that happens, we do not have, there's no horizontal asymptote. And so those would be, here's the examples of all three situations we have when determining horizontal asymptotes. The final type of asymptote we have is what's called a slant asymptote. And what we're dealing with there is we're going to have a rational function, which is f of x equals n of x over d of x, like we've been dealing with, such that the degree of n of x, the numerator, is one more than the degree of the denominator of d of x. It must be, you got to keep that in mind, that it has to be one more. The numerator has to have, the degree of the numerator has to be exactly one more than the degree of the denominator. Then f of x will have a slant asymptote. And then to find that slant asymptote, what we really have to do is we're going to do long division. We're going to divide n of x by d of x, and then you're going to, I want you to think of that, how we would express f of x as f of x equals q of x plus r of x over d of x. When we went through, when we did the long division, how we let f of x, whatever we were trying to divide, was equal to q of x, that quotient polynomial, over the remainder polynomial over the divisor polynomial. And what we have here, if you totally ignore that remainder, this portion, q of x, is going to be the slant asymptote. Y equals q of x will be the slant asymptote on this problem. Let's take a look at an example. In this case, we're going to take g of x, which equals 3x to the fourth plus 2x cubed plus x minus 1 over x cubed minus 3x squared plus 2. And we want to find its slant asymptote. We know it has a slant asymptote because the numerator has a degree of 4. The denominator's degree is 3. Since the numerator has a degree 1 more than the denominator, we know there is a slant asymptote. So I set it up with long division. I have the 3x cubed minus 3x squared plus 2. And inside I put the 3x to the fourth plus 2x cubed plus the 0x squared, because I'm missing that squared term in there, plus x minus 1. Now what I need to do is I need to go and look at the highest term here, so in this case the x cubed and the 3x to the fourth, and I went through and asked myself, what did I have to multiply x cubed by to make it look exactly like 3x to the fourth? And that's where we got the 3x up here. So the next thing I did, multiplied everything by 3x, so I got 3x to the fourth minus 9x cubed plus 6x. And then we have to go and remember to change all the signs. So that's why I have in the red the minus, where I made this into an addition and then a minus there. And then when I combine all the like terms there, the 3x to the fourth drop off, I get 11x cubed plus 0x squared minus 5x minus 1. And now I go through and repeat the process again. What do I have to multiply x cubed by to make it look exactly like 11x cubed? Well, that was the plus 11. And so I went through and multiplied everything by 11. So I got 11x cubed minus 33x squared plus 22. Changed all the signs and combined them. And I got a positive 33x squared minus 5x plus 23. Had a little bit of a problem, and the only way I could correct it was to color it in and just put the 23 there. So sorry about that. Anyway, the result is on this that this portion right down here, that's the remainder. The quotient up here is going to be our slant asymptote. So our slant asymptote in this case was just y equals the 3x plus 11. And I get that from right up there. Now let's take a look at what it takes to graph a rational function. So we're going to start out again, as we have, with f of x equal to n of x over d of x. Again, numerator and denominator. The first thing you want to do is identify the domain of f of x, which really that's going to be wherever we're going to be looking again where that denominator is equal to 0, because those are the values we cannot use. The second thing we want to do is find the intercepts. Well, the y-intercept happens when you put 0 in for x. X-intercepts, the only time a fraction is ever equal to 0 is when the numerator is equal to 0. So to find the x-intercepts, I'm just going to take the numerator, set it equal to 0, and then solve that polynomial. The third thing you have to do is find any holes. Now we are going to be talking about the holes during class next time. So don't worry about the holes right now. We'll talk about that during class. The fourth thing, we have to find any asymptotes. That means we have to look, do we have vertical asymptotes? Okay, we're pretty much the polynomials, the rational functions we're going to be dealing with are all going to be in lowest terms. So any values that make the denominator equal 0 are going to be vertical asymptotes. Does it have a horizontal asymptote or does it have a slant asymptote? If it does, we'll have to identify those. You'll also probably want to find a few additional points, particularly when we're talking about things that are close to an asymptote, just to make sure that you're able to identify the proper behavior that's happening there. And then we're going to sketch that rational function. Let's look at this example. In this case, f of x is 3x over x squared minus 4. And notice on here I've already factored out that denominator. So I have 3x over x plus 2 times x minus 2. Now looking at that, because the domain we know are values that will make the denominator equal to 0, I know in this case my domain is going to be the values, it's going to be all reals except x cannot equal positive or negative 2. So I know I'm not going to be using positive and negative 2, but any other real number will work. The next thing we have to do is identify the intercepts. We find the y-intercept by letting x equal 0. So to find that y-intercept, f of 0 in this case, is going to be 0, 3 times 0, over 0 plus 2 times 0 minus 2, which that result is 0. So in this case, I know my y-intercept is equal to 0. And in this also, with the x-intercept, we just let the numerator equal 0. So to find the x-intercept, I'm going to let 3x equal 0. That is a 3. And when I solve for x, I get x equals 0 there as well. So in this case, really, the x-intercept, there's only one x-intercept, and the y-intercept are both at the same point. My x-intercept and y-intercept are just going to be the origin, 0, 0. The next thing we have to do is identify any asymptotes. Well, in this case, I look at this problem. First up, I'll notice that I do have, again, this is in lowest terms, so I know I will have vertical asymptotes in this case at 2 locations. And it's going to be the 2 locations that make my denominator equal to 0. So I will have vertical asymptotes at x equals 2 and x equals negative 2. So those will be my vertical asymptotes. The next thing we have to take a look, do we have a horizontal or a slant asymptote or neither? In this case, the degree of my numerator here is 1. The degree of my denominator is 2. Since the numerator has a smaller degree than the denominator, I know I have a horizontal asymptote. And that horizontal asymptote is going to be that the line y equals 0. It's just going to be the x-axis. The last thing I'm going to want to do is I want to find some additional points. To find the additional points, I want to put values that are close to my vertical asymptotes. So in this case, what we're going to do is we're going to plug in, we'll put in 1 and negative 1 and 3 and negative 3 into our function f and determine what we get there to find those additional points. So go ahead, I'd like you to pause the video and find the points when x equals plus or minus 1 and when x equals positive or negative 3. So you're going to come up with 4 points. Pause the video, and when you come back, we'll talk about sketching this rational function. Welcome back. When we went through and when we evaluated this function f of x at our various points, when I plug in a 1, you should have gotten -1. When I put -1 in, you should have gotten a +1. When I put 3 in, you should come up with 3 and then 9/5. And then when I put in -3, I should get -3 and -9/5. So those were the 4 points that we have. And now to go through and sketch these. What you're going to want to do is when you sketch this, you're going to want to go and first make a graph, get the grid all set. Now the first thing I do is I put in the vertical asymptote. So I know I have a vertical asymptote at +2, so I draw that one in. And I have another one at -2. So I'm going to draw that one in as well. Okay. I also know that my x-axis is a horizontal asymptote. So I will go and make that into an asymptote as well. Put that in there. The next thing I'm going to do is I'm now going to go and label some of the points that I know. In this case, I know that I cross the x-axis and the y-axis right at the origin, so we're going to go through this point. And now really what happens at this point is the graph, the graph itself is going to match the asymptotes. I know that as I move closer and closer to either 2 or -2, I'm going to either be going way up or way down, because we know that if you have a vertical asymptote, as you get closer to the value of the vertical asymptote, the function values are going to either go up, or go down without bound. So, what I know in this case, I will go and plot some of the other points I know. I know I have a point at 1, -1, so I know I have a point here. And I also have a point at -1, 1, so that puts me right over here. Okay. And so one of the things I can do with this in terms of graphing it, I know that this thing it only crosses the x-axis at the origin. And so I know that there's when I graph this thing, as I move closer to the vertical asymptote, as I come closer to 2 from the left, I know that this thing has to be going down, because there's no way that I could go through this point and not cross the x-axis again to go way up. So I know graphically this function from the origin is going to go down through there, and it's going to go down right next to the vertical asymptote. By the same token, same logic, I can go through and say, as I move towards -2 from the right, I'm going to be doing the exact same thing. It's going to be going up against that vertical asymptote. So that tells me what's happening between the two vertical asymptotes. Now the other thing I know is that I do have a point at 3 and 9/5. So that's like 3 and pretty close to 2. So I'm going to say it's going to be right about here is where we're going to have that point. And now again, in terms of graphically here, as I move far away from the from 0 off to the right, I know that my function is going to be getting closer and closer to my horizontal asymptote. As I move closer and closer to 2 from the right, I know my function values are either going to go way up or way down. And again, by the same logic we used before, I can't go through this point and go down without crossing the x-axis. And I don't have any other places I cross the x-axis. So therefore, I know graphically this function is going to do, in this portion, is going to be like that. It's going to be close to the vertical asymptote and get close to the horizontal asymptote here. In terms of the last point is at -3, -9/5, so it is again pretty close to this point right there. And again, by our logic that we talked about before, this one here, it has to go it's going to end up being close to that horizontal asymptote. So it's going to come like this, and it's got to curve and go down next to the vertical asymptote. I know, let me fill that in. I know this can't go back up because, again, we can't cross the x-axis again. So this right here would be a graph of 3x over x squared minus 4. This now concludes the video that I have on rational functions in terms of identifying the asymptotes. Again, we will talk about the aspect in class to discuss that and how that figures into these problems. But otherwise, most of the time when I ask you to graph these, they will already be in lowest terms, so it's just going to be a matter of identifying where we have the vertical asymptotes, where we have horizontal or slant asymptotes, the intercepts, a few additional points, what that domain is, go from there. So anyway, thanks for listening, and we will see you in class.